My name is Giedrius, and this is my colleague Simonas, and we are co-founders of Icybit, and today we are going to present to you one of our internal projects, which is namely the geo-spatial data clustering engine. So various sources predict that by the year 2020 there should be about 30 billion sensor-enabled devices connected to the internet, and as you all know, usually these devices are very mobile and generate vast amounts of data that have the so-called geolocation element within them. And a lot of companies around the globe are trying to extract value from this fact by searching for various business analytics solutions. For example, given IBM, they have been performing research for the last decade on the subject. Or city labs that are actually analyzing traffic congestion within the United States, or Foursquare that allows you to find places that people mostly visit. However, not always it is easy to find valuable solutions and valuable ways to extract this data. For example, given the Orange Telecom company example, they actually give away vast amounts of information generated within their private mobile networks for free to researchers worldwide in the hope to find researchers that could actually find a way to extract value from this data. And that's why we've decided to build the geo-spatial data clustering engine, whose sole purpose is very simple. We take in a real-time stream of geospatial data, streaming from the mobile operator, and we extract congregation areas of people within cities in real time. So this could be used, for example, let's give an example of, imagine all of you sitting here right now and you would enjoy getting that 50% discount for a laptop PC. If only Acropolis knew that like 150 data scientists are sitting right now across the street. So that's where we come in. We actually allow business partners to locate the clusters of people and contextualize the information to tell them what are the people actually doing there, where did they come from, where are they going. This can also be used in terms of mass disaster prevention, or for example to perform some predictive analytics and help businesses decide on where to place or locate their shops and where do people of most interest are located at any given time. And in order to build such a system that could process these vast amounts of data, we had to analyze the existing solutions within the market. So because we are a startup, we need to rapidly prototype our solution. And the first thing we looked at is Apache Hadoop. However, it was ruled out because it's mostly used for batch processing, and in our case we needed to process streams of real-time data. Then we looked at OpenMPI, which is actually a very powerful distributed computing framework. However, it is mostly used in supercomputers or other localized clusters. And our system should run in the so-called wide area network, so it was also ruled out. The closest to what we came to using was Apache Storm, a distributed real-time analytics platform open sourced by Twitter. However, after 2 months into developing the prototype using the Apache Storm platform, we hit a brick wall when the communication between the processing nodes, or as they call it, vaults within the system, was very limited when repetitive and high-performance processing had to be made. And this is where we've decided to go die hard and implement everything in low-level C language and build out a distributed peer-to-peer topology and do a lot of other crazy stuff that they don't show you on TV and don't talk about at the university. And we went a long path, and my colleague Simonas will now present you two of the core algorithms that we use within our system.
So yes, so as Giedrius just mentioned, that we've kind of been pretty excited about Apache Storm, and you're doing something, you really hooked up with that, and then you hit the wall. How many of you have been in the situation when you're kind of hitting your head into the wall, and you just have to go through all the frustration? So we started to do everything from the scratch, and we figure out, let's just go from the very, very basics. So what is the data clustering? basically what you do, you take all the, you get the data set, you remove all the noise, remove all the outliers, and just get everything what you need. For example, here for the two-dimensional data, you just remove all the outliers, all the noise, and just identify what you need, the cluster cells, some kind of grids that are close by. So that's basically how we started from that, and it sounds pretty simple, but when you get to the data stream, it's not that simple anymore, because like Giedrius mentioned, there's gonna be like 30 billion devices with that geolocation element. They generate vast amount of data that can't really be stored in one place. So from there, we kind of get two challenges: data volume, and as well you can only process it in a single pass. You cannot really store it anywhere. And since we are analyzing the behavior of the, like, trying to do approximation of the entire population, we kind of figure out that we have to reflect all the dynamics. So our data gets the spatio-temporal element. Basically what it means, that the information exists both in space and in time. We have to keep in mind both of the elements. So since we figure out those challenges, we kind of started to look for the algorithm that would be capable to deal with all the situation. And we thought, people are doing that, they know the solution, we just Google that. It wasn't that easy. We started off with the clustering system. It's a pretty popular system. It was created for the data stream clustering. It does the summarization part of the data, so we don't have to store all the data we need. We just take a small summary and just cluster it. But then it has a couple of drawbacks. First of all, it's only capable to identify clusters of a circular shape. When we are talking about the people, they just act randomly. So we thought that we cannot use the clustering system. And as well, you already have to have insight about the data that you're processing even before starting to do that. Since again, it's a people, since they're random, we could not use that. So that's where the excitement kind of got down. And I think that most of the people can relate to that. Then we find another group of algorithms that are based on density. The most popular one is the dbScan algorithm. It takes every single record, just looks for the neighboring areas, and in that way identifies the clusters and removes all the noise. It sounds pretty exciting as well, but then we figure out that you have to store every single record of the data and process every single record. As we saw in the challenges, it's not that easy with the data stream, so that was the second time we hit the wall. And then we figure out that if you take dbScan and take the clustering, we can find something in the middle that would work. And luckily some of the guys thought about that before us. So they invented this D-stream algorithm that we had to modify. But basically what it does, it takes all the data stream, it summarizes it, so reduces the volume of it. As well, it introduces this decay factor that can make a difference looking at the old data and new data, so they're not equal anymore. And how it does it, I'll just tell you in a second. So first of all, just to start off, it divides the area into so-called grid. The grid size that we choose basically defines the precision that we want out of our clustering result. And just to give you an example, if we want the precision of 100 square meters, we divide the whole Earth into those grids. We get more than 5 trillion of grids, and that's how we by ourselves are creating big data, so we are not solving the problem. But data stream kind of deals with that. It has this online component. So basically what it does, when the new record comes, it just maps it to the grid accordingly to its coordinates, and then when the second record comes to the very same grid, it doesn't create new data, it just updates the density of the grid. So as more records come, density increases. As the time passes, density is getting reduced by the decay factor that you mentioned before. So it's pretty simple actually, but it's clear. So after that, we have the second phase of the algorithm, the offline part. It identifies the sporadic grids, the ones that are not relevant anymore, and just removes them. Then it does that identifies the most dense areas, the center of our clusters, and just builds up the cluster just around them. It's pretty easy. And that was exactly what we needed, but then we thought there is one more problem. Like, Giedrius, let's do some calculation, right? And how much RAM memory, like random access memory, do we need? Again, we do not go like Lithuania size, we go the world size. And after doing the calculations, we're like, you know, it's like 6 terabytes of random access memory. We have to do something about that. So that's when we hit the data structure problem. There are a couple of data structures that can cope with all this kind of space. It manages the space pretty efficient. So there are quad-tree and R-tree. We had some experience with the quad-tree data structure. In some edge cases it doesn't perform really well, and those edge cases are pretty popular in our field. So we thought that we cannot use it, so we went to the R-tree. I probably won't tell too much how it works, how it does all the stuff, you can Google that. But when the new record comes, like from the very root of the tree, it gets wrapped up with a minimum bounding rectangle and paired with other elements that are already in the set. So basically we don't waste any space, we don't save anything that is not necessary. And it's pretty optimistic to think that even with this data structure, you could hold the whole data in one server. It doesn't work like that. So we implemented the horizontal split method. When tree gets too big, we just split it horizontally. Part of the tree gets transferred to another server, and then they just communicate through our protocols. Even though it's still too tight, so we implemented vertical split. When it gets too tight, it splits the lower part and just transfers to the next server. With this kind of situation, we can actually scale our data structure as much as we need. One problem is probably just the resources that we can afford. But considering all the servers that we need to hold all the structure, considering all the clustering algorithms, we thought that that's where the real fun part starts. We have to make everything to communicate. And that's where the Giedrius are going to talk about the topology.
So as Simonas mentioned, for the components to work, they have to have some sort of medium. That is for example, processing node in which to run. And as the system architect, the first thing you have to consider when implementing a distributed topology is whether your system is going to be centralized or decentralized. And in the case of a centralized system, as you can see on the picture A, we've got a master node in the middle that is actually responsible for processing all the communication that is happening within the system. And in this case, imagine we have a remote procedure call to execute that originates at the node A, goes to node B, to C, D, and all the way back. We would need 12 network hops to perform this operation. While in terms of the distributed decentralized topology, we have no middle node, no master node. All the nodes are equal peers, and they are capable of performing the same functionality. And the same remote procedure call would, in this case, take only 6 network hops, thus increasing the performance by 50% and potentially the throughput of the whole system by also 50%. So it was clear to us that we should have to go with the decentralized solution. However, one of the difficulties of dealing with distributed peer-to-peer topologies is that when the node number increases within such a system, actually managing all this data is very, very difficult, and you have to have automated processes that manage these nodes. So in terms of the geospatial data clustering engine, it is formed of 3 types of distinct nodes that form the core. We call these nodes cells, and we've got a distributor cell that is actually responsible for distributing the data within the internal system. Then we've got the builder cell, which operates the R-tree data structure previously mentioned by Simonas. It's actually responsible for building a geometrical index from the geospatial data that comes into the system. And then we've got the cluster cell that's periodically communicating with the builder cell to access snapshots from the R-tree and to perform clusterization using the D-stream density-based stream clustering algorithm also described earlier. Another interesting point to note here is that we can see two different communication flows that occur amongst the nodes within the system. So we see a control flow, which is used by the nodes to self-coordinate the system. That is to check on the heartbeats of each other, or for example, whether a node is alive or dead, or whether a new peer arrived within the system to detect it. And in terms of data, we have the data flow that is actually defined by the task of performing geospatial data clusterization. And it is minimized in terms of connection. As you can see, there is no need for the distributor cell to open up a data channel to the cluster cell, because they actually never have to share information. So this is an optimization that we have implemented. And as you can imagine, to actually manage all of this, it soon became very, very difficult. So we had to actually implement a couple of protocol drafts to actually specify how the system behaves. And we've got the lower level protocol, which actually describes how, given a bunch of nodes, processing nodes or computers, let's say servers, how should they connect with one another to assemble a distributed and structured peer-to-peer topology. And then we've got the higher level protocol that utilizes the functionality of the lower level protocol and describes how should the nodes share information with one another to actually perform the geospatial data clustering task. So to point out, the lower level protocol allows us to actually build a system that can do whatever is necessary in a peer-to-peer fashion. And the higher level protocol describes how they should behave in our specific case. So to illustrate the mechanisms of the lower level protocol, imagine we have a TCP/IP network in which we have 4 nodes available to us. And at the beginning, they actually have no state, they have no role, they are completely equivalent and unaware of each other. And as time goes by, we actually specify mechanisms for them to locate autonomously each other within the system, open up connections, and form the so-called overlay network. The overlay network allows the nodes within our system to actually communicate with one another easily within their boundaries and locate new peers and so on. Another interesting fact that we have implemented is our protocol allows the system architect to specify an heuristic function to tell the nodes how should they optimize the system. For example, in our case, let's say we want to optimize for throughput, decrease CPU usage, RAM usage, and in such a case, the cells can autonomously decide on what roles should they take. And for example, in this case, you can see that the nodes decided that there should be, given 4 nodes, there should be 2 builder cells, probably because building the geometrical index is more costly than the other types. And in terms of the data flow, we have, for example, the data provider. In our case, it's a mobile network operator that can actually stream us, for example, call detail records from each of our phones. Or let's say it's an IoT device or mobile application that usually produces raw and structured machine data. And we've got the data aggregation service, whose primary purpose is to collect this data, structure it as specified by our higher level protocol, and then pipe this structured data stream to the distributor cell, at which point the data actually enters the inner system. And on the completely opposite side, we've got the cluster cell, which actually broadcasts primary clusterization results to any external system components that are actually interested of listening to this data. For example, the data analytics service that can actually act in one of 2 ways. It can either pass this data results as is to, for example, non-system components such as the data display client or some web application that we want to implement based on this engine. Or it can perform secondary processing, that is, for example, offline processing. And in the future, we intend to contextualize all the information, for example, to detect why have the clusters formed, what are people doing there, where are they going, and where did they come from. And this can be done, for example, by using some machine learning techniques or performing logistic regression or utilizing some persistent data store to process the data in another snapshot. as it's now not a real-time stream of data, but you can perform repetitive processing. So this is actually the overall architecture of the geospatial data clustering engine system. And as I said before, we have a data provider that actually provides data to the data aggregation service, which then pipes the data to the internal engine, which is circled around with red dash. And the distributor cell then forwards the data to the builder cell, which builds the geometrical index using the R3 data structure, and then communicates periodically with the cluster cell that actually performs the actual clustering and extraction of clusters from the data. Then the results are forwarded to the data analytics service, which can either modify the data or not, and pass it on to the data display client, which we have implemented for demo purposes. So as you can see, big data and data science in general is not about the data all the time. It's actually quite a vast topic, and we actually had to learn algorithms and, for example, networking in depth to actually build such a system that could process vast amounts of data. And now we're going to show you a short demo of how it all works in action. So we're actually using the Docker containerization platform, if you have heard of it, to actually launch the aforementioned different cells, the aggregation service, the web application that we've built for these demo purposes. And as you can see, we have running a virtual topology of 6 distinct nodes within our computer. To better imagine the situation, you can imagine 6 different computers running different software.
As again, when you try to do a demo, something doesn't work. But it should.
We'll reboot.
Maybe it's because we use some CDN for the web app.
Could be.
So yeah,
We've got a backup plan. Record that.
So all the process is working, but the web app doesn't work. So I think I have a demonstration video somewhere also. We'll try to figure that out.
Are there questions? Well, guys are
Yeah,
preparing.
maybe you have any questions while we work this out.
Did everybody understood how it works?
How do you get the data from mobile cellular?
We currently simulate the data, but in the long term we hope to receive it from the mobile operators, as they usually don't use that data for their own purposes.
Does it require some legal rights or something?
Yes, of course, it's very privacy related and a lot of concerns related to that. But it is
So
doable.
like Google has it, like when they use for the traffic jam and so on?
Yes, they perform similar operations, yes. But we use it, for example, to detect people congregation areas within cities. They use it to optimize for traffic, but our solution can also optimize for traffic, as it can detect vehicles and people within them in the same way.
So how is our solution different from Google?
Let's say that we use a non-invasive method to actually find data. For example, as you have your phone in your pocket, it actually sends records to the cell towers. They register your location periodically, and we can actually access that data in non-invasively. Let's say you don't have to install any web app like Google Maps or something on your device, and we can actually access that information. And as I mentioned previously, Google actually does this only for traffic optimization. And what we're trying to do is we're actually trying to approximate the behavior of the entire world population, and that's actually not being done so much right now. And as I mentioned, a lot of companies are performing research and searching for ways how to do that, because there's an enormous amount of value within this.
Okay, so I managed to run the app. So
Oh, okay, so we'll have a live demo, that's awesome. And as you can see, we've performed a post request, and now it's actually generating simulated data. The red dots represent, for example, people within the city, and the records actually, as you see, as they come in, the clusters actually follow, and they are fully dynamic, and as records, the red dots represent, for example, the forming people congregation area. Let's say there are a lot of mobile devices at that region, and as the mass moves, the clusters actually adjust dynamically in real time, and in such way we can actually track masses, for example, to locate, to actually analyze how people behave within the situations of mass disasters, or for example, to prevent them, or as previously mentioned, to monitor traffic, or actually decide on what people are doing at that place. And another important thing to note is that we actually contextualize this information, the clusters, even though the context is fairly slim right now, we show the average density, but in the future it could be used, for example, to approximate how many people are within the region. For example, say, how many people visit this restaurant here, or for example, how many people are now in Kid Club sitting right here. And we could actually detect a cluster of people right now as we speak. And for example, someone would enjoy knowing that there's an event like Kid Club going on right now, right besides them, and maybe they would drop by to listen to a presentation or whatnot. And that's probably it. And another important point to note is that we optimize for performance here. And given this very laptop PC, this old school laptop PC, we can actually, our algorithms and the system can actually process the amount of data that is currently being generated by the entire Baltic region, all the mobile operators located within those regions. So we're actually heavy on expanding globally. So thank you, and maybe you have any questions regarding the system, or any other questions. Yes.
So I mean, data from cell towers, it's not as accurate. So is it enough for you, or do you still need GPS location?
Yes, so to repeat, is data from mobile operators accurate enough, or do we need GPS? So there are currently research papers on triangulation methods that could actually improve the accuracy down to, say, 50 meters. And the primary purpose of the system is to detect masses of people. So we usually don't need to go down, to increase the precision below that point. But yes, that's a good point. And another method that we could use is, for example, to develop a mobile application on top of this engine, so that everyone using it, we could collect, for example, GPS information and have increased precision. The system now allows precision to cluster precision down to 10 meters. So, if that answers your question. Any other questions? Yes.
How long did it take for you to implement this? How many iterations?
So how long did it take to build something like that? We actually spent 3 months building this prototype, of which we spent about 2,000 hours coding. So it was a bit more over 8 hours each day. So yeah, but there's actually a lot more work to be done, as you can see. It's mostly now, it's just a base engine and optimized algorithms on which to base future business applications. Yes.
What about mobile operators? Are there any we have government research about them? Can they supply the data as fast as you want?
So to repeat the question, can mobile operators keep up with supplying data for the solution? That's a matter of research that we are yet to perform. We believe that their infrastructure is a bit outdated, but we believe that we can actually build integrations to actually stream this data in real time into the system. And in such case, yes, they could actually provide this data to us. And there's actually research performed in Deutsche Telekom. I think that actually the telecom company is trying to achieve something like this. to actually analyze the data in real time, not in the past as it was generated previously. Any other questions?
So it looks like you will be also doing integration that other partner will send to us data.
In the initial phase, yes, that's the work that has to be done for the system to operate. Unless we are mistaken and they have already the infrastructure for this. Any other questions? We're running out of time. No? Good for one question? Okay. So,
There's no last question.
no last question. Then thank you for your time.
I have one question.
Yes.
So Icybit OÜ